Hi guys, this is Mr. Mugala again on Kirchoffs laws. Now this time around I'm looking at Kirchoffs laws, THEVENINS theorem, NORTONS and substitution method. But of course, like I mentioned last time, that we're going to look at a furthermore example, a more complex example that tries to address the issues at hand. So really quickly, let me dive into the question on Kirchoffs law. So the question, actually, let me just go. It says that use Kirchoffs laws to calculate the current through the 8-ohm resistor in the circuit. And the circuit under discussion is the circuit right here. So what we're trying to do is to find the current that flows through the 8-ohm resistor. Now you can see here we've got 3 battery DC sources. And you can also see that these battery sources got a positive that points this side. And this one has got a positive that points this side, and this one has got a positive that actually points this side. So the first thing that we need to do is to try to see if we can distribute our current. But I want to say that, as you can see, we have, how many loops do we have? So we've got that. So we have the first loop, the second loop, and the third loop. Okay. Now, if we're going to loop going this way, so we have identified that these are the loops that we'll actually be dealing with to be able to identify. But of course, we may have more loops. Of course, this is 1, 2, 3, but of course there are other loops as well. So you need to know. So in order to carry out an effective current distribution, then of course you need to start with a current I, for example, right? That starts from this source. It doesn't matter. These are also, we can also start from anywhere, but we choose, for example, to start from here, so that we can do our effective current distribution. The boy, you're making noise here. So now, what are we going to do? So what we're going to do now is we are going to start with the current I. And when we start with this current I, it will flow through this point. And once it reaches this junction, what is going to happen? Some current will go through this way, and some current will go through that way. Now, for example, if we choose that I1 goes down, then for the purpose of what I've shown even in class previously, to do a proper current distribution, then what goes through I4 is, what goes through 4 ohms is I minus I1. Alright, and so when we see here right now that the current that comes here and it hits this junction, I minus I1, we can have I2 go through this side, and we can have I minus I1 minus 2 go through that way. So for example, you can see if I have that as I2, then I can have the current that it goes through this direction as I minus I1 minus I2. Now this is the current that goes through all the way through this branch. It's the same current that will go through all the way till it reaches that junction. And you can see here there's this current, it goes through all the way down, it comes all the way till it reaches that junction. Now it's not difficult to see that this current that is coming in plus the current that is going through their side and is coming into the same junction, they will add up, and if they do add up, they'll give I minus I1. So you can see here that I minus I1 could be the resultant current, because you can see this current will hit this point, and this current will go round, and again it will come and hit that point, and we have that current going through. So I minus I1 again, which is this same current, is the current that is flowing here. So this current will come and will hit this junction right here. So now if it hits this junction, we expect that I is the current that will go, because this is the current that we started with. Now look at that. So if this current comes in, and that one is already coming in by nature, and if the two add up, they'll give the same current I, and it's the same current that goes through all around the loop. So that's how come you know that you've done a proper current distribution. All right. And guys, if you don't understand this, just repeat my video to get a furthermore understanding, but that it just gets as easy as that. So when you do things this way, first of all, the advantage is that you will have the minimum number of unknowns, right? And then you'd also make sure that you cut down on the unnecessary equations that can be created if we're just giving currents as I1, I2, I3, I4, and I5, because the more we give that, the more we need current loss. But this is a neat way of trying to distribute the currents. Now, what's the second thing is? The second thing is we need to start giving polarity to our resistances and the voltage drops across the resistances. Now, just like I said, for passive element analysis, once this enters this node, it leaves a plus there and a minus there. So if we have to look at the voltage drop across that one, can be 2I plus 2I, because you know that I times 2, because you know that's his plus and that's his minus. So we're going to create that. So again, if we look at that, this is plus because of course I1 is multiplied by 4, and then we can have I1 4, but it's going to be plus because this is going to be plus and this is going to be minus. And if we again look at 20, if we're going to look at the way we're going to loop, the way we are looping, then this one we're entering from the minus, so this one will be minus 20, and this one will be plus, and that one will be plus as well. Now if we look at that as well across the 4 ohm, the voltage drop across the 4 ohm will be that, and if we look at the voltage drop across the 2 ohm will be that. Now here guys, there's a small mistake here, because here it's plus of course and minus, but I should have written I2 2 ohm, so please take that one into consideration. I'm going to rectify that. Now if you also look at what is going through that this current is the one, this is alright, so this is the current that is coming to this, so it's going to be plus times the 4, so that gives you that. And here of course definitely that is a plus, and this is I minus I1 minus I2, and that gives us that. And in terms of the way we are looping, that could be minus 4. So here it's true that we're going to have a loop for this equation and a loop for that equation, and so we're going to have an equation for this loop, an equation for this slope. So the equation for this slope is plus 2 plus I14 minus 20, right? It's just self-explanatory. And of course here as well we're going to have plus, if we start from there, plus I1 minus 4 plus I2 2, then we have 8 volts. So here it doesn't matter, there's no resistance here, and then we go that way and we'll have traveled the loop, and again that will have traveled the loop. And guys, if we look at it in terms of the simulation that we get, so the simulation results are giving us that I is equal to 38.92 and I1 is 3.058. The minus is just the way the ammeter should have, the direction of current should be the other way around. So this is 0.432 and this is 0.405 is the current that is going through the 8 ohm resistor, the current that we're looking for. So these are the results that we get in the simulation. So I say that the first point is to start with the current I and then distribute it across the such that you obtain the same I. So after you distribute, you go through, you go round, you have to get the same current. And here for the rules of summation of current entering the junction is equal to the summation of currents leaving the junction. And these are the same equations that we're talking about. So for loop 1 you get that, for loop 2 you get that as an equation, and also for loop 3 you can get that as an equation. So you need to verify, go through these loops, and I've shown you how to do it before. Now we can say that loop 1 KVL gives us that, and if you want to solve really for this, well, the approach I used is that now I can make I the subject of formula and solve it for I, and that's what we have. And for loop 2 we can see here, we once you simplify loop 2 equation, it should come to that, and for loop 3 it should come actually to that. And if you solve for replacing I in loop 2, if you replace I in loop 2, this is the equation that you get, guys. And if you solve, you should come to this equation that gives you that. And if you replace I in loop 3, you should have that, and that times that, and that gives you 4. And if you solve that, you should have the final equation that gives you 36I plus 14I2 is equal to 116. Now, solving the two simultaneous equations that you solve, solving the two simultaneous equations, what we have now, we have 16I1 minus 2I2 is equal to 48, and we should have 36I plus 14I2 is equal to 16. So now what are the results that we get? Well, so once we've simplified these equations, we should be able to get I1 is equal to 3.054 amps. Now guys, you can solve these simultaneous equations. You can use the elimination method, you can use the Cramer's rule, which all of you maybe may understand. You can also use method of substitution. Again, at this stage, this is an equation that has been simplified to a two equations, so this is very easy to solve according to this question. So if I1 is equal to 3.05 amps, I encourage you to go through it and try to verify the results, and you can see that I2 is equal to 0.432 amps. And you can see that I now, since we had this equation, the first equation said that I is equal to 10 minus 2 I1. So I just replace where I1 is, and I can have that is 3.9892. Now, if you look at the current that flows through the 8 ohm resistor, guys, and if you replace that we saw it here, right here, that the current that flows through the 8 ohm resistor, let me just go back to it, is this current that flows through like that. Now you saw that this current, according to the previous range, this is I minus I1 minus I2. This is the current that goes through and flows through that resistor. So therefore, if I try to go to our simulations, our results, it's not difficult to see that eventually we have all the currents actually verified, as the switch is the same as, of course, this is showing that 0.6 is approximately actually the same. If you get I minus I1 minus I2, you should get 0.406 according to the calculation as seen in the simulation. Now this is really the same, because if you look at I, for example, in the simulation, I is 3.892 amps, and if I come to the simulation results, I get 3.892, and 3.054 is the I1 that we solved, and this is the I2 that we solved, so 0.432. So guys, this is how I was really quick, and I'm hoping that you will actually get it. All you need is just to solve. There's nothing difficult here or complicated, but you just need to go through the equations, verify them, and make sure that you get the correct results that you're looking for. Now, I'd like to thank you very much for viewing, and this is what I really wanted to show you as another way to solve, as a very flexible way to solve these Kirchoffs laws. I'd like to thank you for viewing, and make sure that you practice this equation for yourselves, because I usually bring it in a test or exam, sometimes just to see how students are able to solve complicated circuits. But I'd like to thank you once again, and we'll see you in the next lessons. Now, in the next lessons, you'll see me use the same circuit to analyze the Thevenin's theorem and the Norton's theorem, the Thevenin's theorem, Norton's theorem, and substitution theorem. Thank you so much, guys.